So many of the units we use will be based on the metric system. For any base unit, there can be a metric prefix. I've listed the major ones I'd like you to know here. Mega always means a million, kilo 1,000, deci 1/10, centi means 1/100th, milli means 1/1000th, micro means 1/1,000,000th, and nano means 1/1,000,000,000th. Okay, so let's look at length and its units. I have a meter stick about the length of my arm. Up close, it is split into 100 parts, each the same length, about the width of a dime. These are called centimeters, and each centimeter is divided into 10 equal parts, each about the thickness of a dime. These are called millimeters. Comparing these units, we see that they all have the base unit meters and a metric prefix, except meters, of course, which has no prefix. Centimeter is 1/100th of a meter, so centi always means 1/100th. Millimeters are 1/10 of centimeters, and 1/10 of 1/100 is 1/1000, so the prefix milli means 1/1000. So you need to know not only the units meter, centimeter, and millimeter, but also their metric prefixes and what multiplication factor each prefix stands for. It turns out there are a few other metric units that are so common that I want you to know these also. Going down the table, a micrometer is too small to see. But with a microscope, you see microorganisms like bacteria that are about 1 micrometer long and form the basis for the study of microbiology. The metric prefix micro means 1/1,000,000th, and a micrometer is 1/1,000,000th of a meter. We will also encounter nanometers when we study the wavelength of visible light. The prefix, a multiplication factor, the prefix represents a multiplication factor of 1/1,000,000,000. Okay. Now I should also mention a kilometer, which is the length from Black Hawk College down to Route 78. It has a metric prefix kilo, which always means 1,000. It's 1,000 meters. And then, in addition to knowing the metric prefix and the multiplication factor, the abbreviations for these units are important as well, and I've listed those. Okay. Finally, in the last column, what I'll show is the useful relationship. A kilometer is 1,000 meters. 100 centimeters is equal to a meter. 1,000 millimeters is equal to a meter. 1,000,000 micrometers is equal to a meter, and 1,000,000,000 nanometers is equal to a meter. Volume is a measure of the amount of space occupied by an object. The metric system base unit is the liter, about as big as a football, although here I've pictured a Nerf ball that's about as big as a football. The most common other metric units are deciliter, 1/10 of a liter. This is the size of about a tennis ball. The milliliter, 1/1000th the size of a liter. That's the size of about a peanut. And the microliter, 1/1,000,000th of a liter, that's about the size of a few grains of sand. We see that we still have milli as a metric prefix that means 1,000, and micro, the metric prefix that means 1/1,000,000, just like they did for length. I have just added a new one. We see a lot of volume that is deci. which means 1/10. There are abbreviations associated with these. Notice that in the abbreviations, the liter part is designated by a capital L. And what I forgot to mention previously, but I'll mention now, is the metric prefix micro is represented by the Greek letter mu that looks like a U with two sides coming down. That's not actually a U, that's a Greek letter mu that means micro. Once again, there's a relationship of the base unit to the number of metric units, and that's shown in the last column. So, just like for length, there are some common instruments I would like you to know for measuring volume. The beaker is just a cylindrical glass container. This is a 1 liter beaker. It holds a liter, but notice that it's marked off in smaller units that go up to 1,000. The smaller units are milliliters. 1,000 milliliters equal 1 liter. You will use this relationship, 1,000 milliliters per 1 liter, a great deal in chemistry. Now, if the neck is narrow, it's a flask. Two types are here. This is an Erlenmeyer flask, and this one with the skinny neck is a volumetric flask. The big difference in these is accuracy. Anything called volumetric is more accurate. This will measure volume to about plus or minus 1 milliliter accuracy. The Erlenmeyer can only measure it to about plus or minus 10 milliliter accuracy. Okay, so those are the flasks. So when you're mixing up solutions, always mix with volumetric flask, not with Erlenmeyer. Next on our list is the graduated cylinder. Okay, this is a graduated cylinder. Graduated in the lab always means that there's a scale marked off in little lines like a ruler. Okay, the little lines here are marking off differences in 1 milliliter, so these are milliliter graduations, and this goes up to 100 milliliters. When you're measuring volume, the graduated cylinder is more accurate than the beaker. They're both sort of the same shape, but this is the one we use for measuring volumes rather than a beaker. For smaller volumes, we will often use pipettes, and there are a variety of these. So let me get some of these out. Maybe I'll move these off to the side. All pipettes are used to suck up liquids. So I have a liquid here. This one does it with a plunger. Have the plunger, and the plunger goes on the end. And all you have to do is put the point into the liquid and cause some suction, for example by this plunger, to suck up the liquid. I will suck the liquid up to the 0 point on the scale, and then when I want to get my small volume out, I'll just count down how many milliliters I let out on my scale. Okay, so that's how I get volume with a pipette. Now the other thing I'll bring to your attention is that this pipette just needs suction on the top. And there's a temptation to use the old-fashioned suction method, just putting this in your mouth. Do not do that. That was done in another place and time, but it's not done today. It's too dangerous. So mouth pipetting, if you do that, you are risking to be asked to leave the laboratory because you're too dangerous. And if you're on the job, you could be fired for something like that. Safety is a very important aspect of chem labs. This is a nice little disposable pipette. All you got to do is pinch the top. That generates suction. You can suck up the liquid and then let out how much you need exactly. I need that much, and then let that out. A pipette with a bulge in the middle is a volumetric pipette. I'll just mention that these volumetric pipettes are used for very accurate measurements. And then the last pipettes I'll show you are called micropipettes. These days we have to use such small volumes that we need a pipette that will measure microliter increments. So this has a little wheel on it. I can set the value. I've set it at 0.8 here, and this will take 0.8 milliliter volume. I'll put the plunger down on the top, let the liquid soak up right here. I'll also bring to your attention that another micropipetter here is actually set at 1 microliter. You probably can't see it, but I wanted to let you know that about the smallest volume we can measure these days is 1 microliter. It's in the little tiny tip right there. Okay, so we have pipettes, graduated cylinder, flasks, both Erlenmeyer flask and volumetric flask, and beaker. There are other measured units we will pick up along the way, but let's add mass here as one of the more basic ones. The base unit is a gram, which weighs about as much as a dime. If we go to 1/1000th of a gram, we get a milligram, which weighs about as much as an eyelash. And if we go 1,000 times more than a gram, we get a kilogram, which always weighs about as much as a 32-ounce drink. Once again, we have abbreviations for each of these units that are important to know. There's a metric prefix that's the same as before. Kilo means 1,000, milli means 1/1000, and the relationship to the base unit is shown as well. Now, throughout this lesson, I will use the word weigh. Technically, mass is not weight because it doesn't change when the force of gravity changes, like when you are on the moon. However, as long as we are on the Earth, mass is proportional to weight. So the weight measured by the balance, these instruments we use to measure weight, can be directly converted to mass in grams. I will tend to use the words weight and mass interchangeably. So as a rule, we will use two types of instruments for weighing grams. These are the top-loading balance and the analytical balance. Let's look at the top-loading balance first. That's what I've got on your picture there. It's just like a bathroom scale. You just put your weight on it and it reads the weight. In this case, out to the second decimal point in grams. However, like all instruments, it needs to be calibrated. Calibration is often called zeroing. We just put zero mass on the balance and push the zero button, which is right here, and it sets itself to showing 0 grams. Once it is calibrated, we just put our weight on the balance and read the value. I don't know if you can read it. It says 1.24. That's how many grams that weighs. Now, if we want to weigh something that's in a container, then we just zero the container. Then we put what we want to weigh in the container. And it just gives us the weight of what's in the container. When we do that, when we zero the container, that's called tearing the balance, and so you need to know that word. The last important thing about balances is that they are fragile and expensive, so you've got to treat them with care. Notice that they have a maximum weight rating. This one is 200 grams. That means that if you put something heavy on the top, more than 200 grams, you can damage the balance. One of the big problems we find is that people want to grab these things and push down on them with their thumbs. Do not touch that balance with your hands and push down on it. You may damage the balance. Now, when you're using the analytical balance, it will look something like this. We see that it can weigh grams to the 4th decimal place. That's to the 10,000th place in grams. That is, it can distinguish weights that differ by no more than 1/10 of a milligram. We'll only use the analytical balance when we need this type of extreme sensitivity. So we will mainly use top loading balance. When we use this, we can still zero it. Okay. And then if we're going to weigh something, we'll have to open the door to the pan and close it, and then we can read the weight. Now along the way, whether we're zeroing or weighing, we cannot let the doors be open at all. They've got to be closed, because even small air currents are enough to throw off this balance. We will also not lean on the table or disturb the table. Small vibrations will throw off the analytical balance, even if somebody walks by and it's not on a very rock stable surface, which we don't have in here. So even if somebody walks by, they can cause the analytical balance to fluctuate. So just use it very carefully and limit all the disturbances around the analytical balance.